AP 120, Chapter 3, Passive Transport. So, uh, it is very important to the function of the cell membrane to have various ways of allowing materials to cross the membrane as well as to prevent materials from crossing the membrane. One category of transportation that can occur across the membrane is called passive transport. Now, passive transport is when materials move along their concentration gradient. So from moving where there's a lot of something to where there's very little of that something, or along the electrical gradient, where something that's positive charge moves to a negative area, or something negative charge moves to the positive area. Because again, as we know in electrochemistry, opposites attract. So that's all well and good, but the most amazing thing about passive transport is there's no energy input necessary. The cell does not have to expend resources to allow this to occur. It will happen on its own. So here is a very basic example of passive transport. In this case, it's a membrane-free example. You drop some dye in a beaker of water, high concentration of dye in the droplet, low concentration in the water around it. Over time, the dye will begin to spread out from the droplet, going from high concentration to low, until eventually the dye evenly spreads throughout all of the water. So again, diffusion, in this case, is movement of materials from high concentration to low, and no energy is needed. It happened all on its own. So with selective permeability, as we know, some materials can automatically cross the cell membrane. And so for those materials, passive transport like diffusion is a very practical way to get materials to move in. So our cell membrane can act sort of like a fly screen on a window. It allows some things to pass through, but not others. So two types of passive transport. We have diffusion, as I just described, high concentration of materials on one side of the membrane, low concentration on the other. And if they can cross the membrane, they will move from high concentration to low. In this case, lipid-soluble solutes, things that can cross that hydrophobic barrier, will engage in diffusion into the cell. Now, it's worth pointing out that technically materials are moving in both directions, in and out, at the same time. However, the majority, the net movement, is from high concentration to low. So overall, things are going from high to low. And it can occur in either direction. Now we have osmosis. Osmosis is a type of diffusion, but it is only for water. So if someone says osmosis, they're talking specifically about the movement of water via diffusion. And so again, high concentration to low, so a dilute solution on one side of the membrane, a more concentrated solution on the other. Water will move from high concentration, dilute, into the low concentration, deconcentrated. All right, so here is a red blood cell. We'll use this as our cell of choice as we talk about movement across cell membranes. So as we know, we have a watery solution both inside and outside of the cell. So the solvent is water. That is what's doing the dissolving. And the substances dissolved in it are, well, actually a lot of things. So we're not going to worry about specifically what, but there are a lot of things dissolved in the water. So the question would be, which way would the concentrate move? And looking at this solution, we see that the arrows are pointing in each direction and they're all equal in size. So the material leaving the cell is the same amount as the water entering. So water exit, water entering at the same rate. So the net movement is 0. So we refer to this as an isotonic solution. The red blood cell is in an isotonic solution. Basically, the concentration of the solution outside of the cell is the same as inside of the cell, so that the amount of water entering the cell is the same as the amount leaving. And of course, cells like this. Cells want to be in an isotonic solution where they are at balance with their environment. Then, for instance, cells could find themselves in a hypotonic solution. So here's that red blood cell again. Now it's in a hypotonic solution. The solution outside is very dilute. inside is much more concentrated. So where's the more solute? Where is the more solute? It is inside of the cell. And so what happens, as we can see, water will enter the cell, cross the cell membrane, enter the cell, flooding the cell, causing it to swell, and in some cases the cell will even burst. And when a cell bursts, that is called lysing. So if a cell lyses, it bursts. So place cells, red blood cells, any cells in a hypotonic solution with water entering the cell very quickly, the cell will swell and lyse. Then we have a hypertonic solution. So hypertonic, the solution surrounding the cell, very concentrated compared to the solution inside the cell. Where's there more solute? There's more solute outside of the cell. And what's going to happen? Well, as we can see, lots of water exits the cell and the cell shrivels. So another word for a cell shriveling is crenate. So this poor red blood cell is crenating as lots of water is leaving the cell. And the crenation can often lead to cell death. Cells do not want to be in a hypertonic solution. All right, so when people are in the hospital and they're getting an IV, fluid is being directly added to their bloodstream, which means the concentration of the solution in the IV as it enters the bloodstream is going to potentially affect the red blood cells in the bloodstream. So the solution in IVs, are they hypotonic compared to red blood cells? Are they isotonic compared to red blood cells, or are they hypertonic compared to red blood cells? Well, I hope you said isotonic. Again, isotonic solutions is the environment the cell wants to be in. So the IVs, the concentration of solutes in the IVs matches the concentration of solutes in the bloodstream. It's a different mix of solutes, but the relative concentrations are the same. All right, I read in a news article a few years ago about a hospital where a technician who was making solutions for IV made a mistake and made the solution 10 times too concentrated, and a number of patients died because of that. All right, here is some practice examples using a dialysis bag. So a dialysis bag is sort of an artificial cell. Basically, it acts sort of like a cell membrane because it allows some materials to cross the dialysis bag and other materials cannot. For a dialysis bag, what decides it is size. There are tiny, tiny, tiny little holes in the dialysis bag, microscopic in size, and anything that is of the size of that hole or smaller can pass through. Anything bigger cannot pass through. So you can do a lot of experiments where you have a beaker with a solution and you put a dialysis bag inside that solution, and in the dialysis bag is another solution. So you got two solutions, one outside of the dialysis bag, one inside, and you can do experiments related to simple diffusion and osmosis. So key thing, of course, when you think about these experiments is to understand how water is going to move. And water is always going to move to the hypertonic solution. So we look here, solution in the beaker, 1% sodium chloride, solution in the bag, 10% sodium chloride. So the 10% sodium chloride is hypertonic compared to the 1% sodium chloride. And so water will go into the dialysis bag. It will go into the solution that is hypertonic. Why does water do that? Well, if we look at the amounts of water, it makes sense. If it's 1% sodium chloride outside, that means it's 99% water in the solution outside. If it's 10% sodium chloride inside the bag, that means it's 90% water inside the bag. And water, via osmosis, is going to go from high concentration of water to low concentration of water. So it's going to go into the bag. And it's small enough it can get through the holes in the dialysis bag. So again, water always goes to the hypertonic solution. All right, so here is a lovely example. We have a dialysis bag with 1% starch solution. It is placed in a beaker with 5% starch solution. So the fluid in the bag is what compared to the fluid outside? Here's your lovely options. Hopefully you chose hypotonic. The solution in the dialysis bag is hypotonic. It is less concentrated. The number is smaller. Hypotonic when compared to that outside. So that means the fluid outside of the bag is what compared to the fluid inside of the bag? Here's the options again. I hope you chose hypertonic. This solution is more concentrated, has a bigger number, has more solute, so it is hypertonic when compared to the solution in the bag. Now, if possible, water is going to move, and water will want to diffuse until the two solutions are isotonic. Often this isn't possible, but basically it means water will move. So where will water move? Will water move into the dialysis bag, or will it move out of the dialysis bag? I hope you chose out, because again, water is going to go to the hypertonic solution. So it's going to leave the dialysis bag and go into the fluid surrounding it. All right, here we have 10% sodium chloride inside of a dialysis bag. So a 10% sodium chloride solution inside a dialysis bag, and it is placed in a beaker with pure water. So the fluid in the bag is what compared to the fluid outside of the bag? These are the options, and I hope you chose hypertonic. Hypertonic, 10% sodium chloride. Pure water. Pure water is 0% sodium chloride. So 10% is obviously higher, obviously a bigger number. So the solution in the bag is hypertonic. When we're talking about the solution in the bag, what is the solute? And what is the solvent? Well, I hope you answered sodium chloride is the solute. Again, when we talk about solutions, they are in terms of the solute. So sodium chloride is the solute. What is the solvent? It's water. For this course, the solvent is always water. For this course, the solvent is always water. All right, and now for the other important question, which direction will water move? Into the bag, out of the bag, or no net movement? Well, I hope you chose into the bag. It's going to go into the bag because water goes to the hypertonic solution. This is the hypertonic solution. It has the most solute. Water is going to rush into the bag. Now, assuming sodium chloride can pass through the bag, which it can, which direction will sodium chloride move? Into the bag, out of the bag, or no net movement? Well, I hope you chose out of the bag. Sodium chloride is diffusing out of the bag. It's going from high concentration to low concentration, going from 10% sodium chloride to 0% sodium chloride. All right, another form of passive transport is facilitated diffusion. Facilitated diffusion means there's a transmembrane protein that forms a channel. This channel, this tunnel, allows for a specific substance to cross the cell membrane, going from high concentration to low concentration. So the movement of this material across the membrane is facilitated by the protein. Facilitated diffusion. Diffusion facilitated by the transmembrane protein. And usually this means it's something that cannot normally cross the cell membrane. Filtration. Filtration is a slightly different way of things to move. Filtration involves, say, pressure, high force moving something through a structure, a membrane that has small holes. And so, for instance, those small holes would then prevent things that are big from going through. Only things small enough to pass through the hole can get through. So blood pressure in blood capillaries forces small things, fluids, electrolytes to leave the bloodstream. Because of the pressure, the blood pressure is much greater than the fluid pressure, the interstitial pressure outside. So it's acting as a filtration mechanism. Small things leave the bloodstream, big things like cells and proteins stay in the bloodstream. That is it for this part of the lecture.